stereoisomers, molecules with more than one stereoisomer, and the implications of that, total number of stereoisomers we have, and how do we physically determine that stereoisomers exist. So that's a question that I'll have to answer. So on the slide here it says take a white or light yellow atom in the left hand and blue atom in the right hand. And then put a red and green ball on there. And so what do we want to do? So I'm holding it like this. You see that the green one is projected towards you and the red one's away. So in the other model here, hold both in the right hand. So you can see that the yellow and the blue overlap. But now look at the orientation of the red and green in this one. The red is towards you, the green is away. So we can overlap two of them, but the other two are different. And so that defines the stereogenic carbon. For the most part in this class, other atoms can be stereogenic, but we'll talk about carbon. And so if carbon has 4 different substituents, then it's a stereogenic center. So the implications of that, notice that I'm holding 2 molecules. So there's a little equation that we'll look through to predict if you have more than one stereocenter, how many stereoisomers in the molecule produce total. So if all 4 of these substituents, or another word that we use is ligand, on carbon are the same, then they produce a compound with the same name. But there are 2 things, right? Like I asked on Friday or whatever, if they're identical twins, a parent would not name their identical twin the same name. You would have Bob and Bob. It'd have to be different. So how do we name them differently? And then physically, if they're the same thing, how do we know that they exist? So the way I'm holding it's kind of weird, so I'm just going to rotate. So when I rotate it, now these are mirror images of one another. So you can see that the reds mirror the greens, the yellow, and the blue are splayed out. So that property is known as chirality. So chirality are mirror image stereoisomers that are non-superimposable. So what your textbook will say is your hands. So your right and left hands. You do that. They're mirror images of one another. There's no way you can superimpose them to be the same thing. So as we talk about this, the model kits will definitely help you understand this. So I definitely encourage you to use them as we progress through this. So what we'll look at is some flat pictures of this, and then how we assign priority to the 4 different groups to differentiate the names. Any questions before we get started here?
I have a question about terminology. So you're calling the carbon as four substituents stereocenter. In lab, I call it a chiral center. Are those interchangeable?
Yeah, so the word chiral center, I prefer stereogenic center myself, but you can call it a chiral center, chirality center. It's all the same thing once you're familiar with the lingo. And so really what this whole concept speaks to is symmetry. So symmetry is pretty important in chemistry, and there's rules, some qualitative rules to it. If you're really into math, like linear algebra, you can quantify the elements of symmetry, but that's sort of beyond what we do in here. The other thing I want to point out is, so like your hands, I said mirror image, but in reality, if you slice your body like in half this way, externally it's a mirror image, but not internally. So you have two lungs, right? So they mirror, they only have one heart. Most people it's over here. Did you know that some people can have it over here? Like their genetics like reverse their internal organs. So that's kind of interesting to think about. But so we'll talk about mainly molecules, but if you start like walking along and thinking like a chemist, you look at any object and ask, okay, does it have symmetry, yes or no? And that'll help you understand this concept a little better. So what I've done here on this slide now is your white ball will be the H, or the yellow on there. And then red, we're going to say it's bromine, green chlorine, and blue fluorine. So overall, we would name that bromochlorofluoromethane. So we see there's 4 unique substituents. They're mirror images of one another, so they're stereoisomers. And the word that we use is enantiomers. So enantiomers are exact mirror images. There's another word that we're going to use probably on Wednesday called diastereomers. And those are molecules that have more than one stereocenter. So we're sort of building up to describe any molecule, basically. So they differ in the spatial orientation of the atoms. So as you saw in the big model kit there, in one instance the red was pointed towards you, in the other instance it was away. So it's the spatial connectivity of the 4 substituents. So an atom, carbon atom with 4 is called a stereogenic center or chirality center. And so one stereocenter gives rise to 2 possible orientations. And so how do we differentiate them? So we learned about nomenclature. So I'll just say IUPAC nomenclature. That's how you name something. And now this set of rules is abbreviated CIP, CIP, and that stands for Kahn, Ingold, and Prelog. And these were the absolute nerds of nomenclature that got together and figured out these rules. And the rules always work if you understand how they're based. So the first thing you need to do is identify the 4 different substituents. And then furthermore, you're looking at only the atoms directly bonded to the carbon atom. So there's 4 atoms you figure out, and then you assign them a priority 1 through 4. The priority is based on atomic number. You could use atomic mass. It sort of tracks the same. It increases as you move across the periodic table, but the rules state atomic number. I never really remember the numbers. I just remember like oxygen is greater than carbon, that sort of thing. But the numbers that you see here, 1, 9, 17, and 35, those are the atomic numbers of those elements bonded to that carbon atom. So you apply the SIP rules, and now from the atomic number, you're sort of reversing to assign priority. So 35 is the largest number, so that gets priority 1. So the lowest atomic number always gets priority 4. So the next thing that we want to do after we do that, before I show the next slide, I'll just preview it. I think I'm holding the left one. I always F this up. So with your model, it's easiest with your model kit, I'll tell you that. As you do more of this, you can do it in your head, but the model kit will help you. You take the lowest priority atom, whatever hand you want to use, and then you have to rotate. So you want the lowest priority projected away from you like that. It has to be away from you. That's the rule. And then you look at the numbers, which way are they rotating? So in this one, we have 1, 2, 3. So that's clockwise, is that correct? And then if we do this one, what way is that rotating? Counterclockwise. So again, you have to follow those rules so you get this exactly right. Now what is challenging is when things are drawn, sometimes the lowest priority group is towards you. So either with your model, you build it and flip it, or in your mind's eye, you bring it around the other way. So really you're looking at 1, 2, and 3, and 4 is away from you. So you have to do that. Then you figure out, is it clockwise or counterclockwise? And so once you do that, you assign the descriptor. And the descriptor is either R or S. So clockwise rotation gives you R, counterclockwise gives you S. Any left-handed students in the class? 7. So 7 out of about 140. So back in the day, I mean, obviously in the population here, you're the minority of handwriting. But does anyone know what the S stands for? Think about like a couple hundred years ago. Sinister, not Satan. So S stands for sinister, which means evil. So back in the day, left-handed people were considered evil. And you probably would have been burned at the stake because it's different, right? So R stands for rectus. So S, that's the root of these. Where the R and the S come from. And so that's how we can now put a descriptor in front of the name to differentiate the two mirror images. So again, you're assigning priority. 4 is the lowest priority based on atomic number, and then the table is just for you to fill in to get the sequence correct. So the question really is, if they're mirror images, so look at the property, then there's the R stereoisomer property, and then the S stereoisomer. The molecular weight is the same because they have the same molecular formula. The melting point, the boiling point's the same. The density's the same. The C13 shift of each of them is 82. The H shift is 7.2. So even if you had two samples of each pure enantiomer, they're giving you the same data. So how do we know in reality that two of these actually exist? So the R and the S, that is a human construct that these three guys thought of on how to differentiate the name. We know they exist physically based on this piece of information here. See within that parentheses, the negative or the positive. And that refers to the direction in which the molecule will rotate plane polarized light. So did you guys use polarimetry in lab? You remember what molecule you measured? Homecoming has flushed out all this knowledge. I think it was probably glucose, maybe. No? So you have this little polarimeter about yay big. You put a graduated cylinder of a solution, it shoots light through, and then it spits out a sign, plus or minus, and then a number. So two pieces of information. And so the polarimeter is the instrument that is used to measure what's called specific rotation. And that is, for our intent and purposes, the only thing that differentiates these two molecules spectroscopically. So as a brief review of polarimetry, it's a classical instrument in the sense of, in the 15 and 1600s when, these rich noblemen were studying light and looking at the planets in the sky. So my kids and I went to Zubu at the zoo last night, and you could see Venus pretty clear. I mean, it's pretty bright. I have an app that, okay, that's Venus. It's really bright. So people would track these planets as they move through the sky, right? And then they started developing lenses to put in telescopes and thinking about light and how far away things are. And then as science progressed, it was noticed that, some crystals would diffract light differently. And so that's how polarimetry came into being over a couple hundred years. But the instrument, basically what it's doing is it's taking light, which is composed of an electric field and a magnetic field. So see how these arrows, these are vectors, they're 90 degrees to one another. So light has those two vectors associated with it. And so white light is pretty much in every direction for those vectors. Anyone got some shades on, some sunglasses? The reason that sunglasses work, there you go, is there's a molecule in there that polarizes it. And it's essentially filtering out, certain wavelengths of light. So the polarimeter is doing that to give you light that's plane polarized. So you don't have all of these different sort of shades or wavelengths of light. You just have one, and it's going through your sample, and the molecule is going to tilt that light one way or the other. Now, when I say that, don't confuse the direction of that tilt with R and S. They're two very different things. So light that's tilted to the right as it comes out of the instrument, so that would be clockwise, is called dextrorotatory or plus. If it goes to the left, it's called levorotatory. So again, that counterclockwise, clockwise has nothing to do with R and S. So specific rotation has the sign, which we're concerned about, and then a magnitude. And again, these are experimentally measured. You absolutely cannot predict, is it going to be plus or minus, and what that value is. You just make the sample and run it. The instrument spits out that data. Enantiomers have the exact opposite sign. So if one enantiomer is plus, the other has to be minus. The value or the magnitude of the rotation, it is what it is. But say if one is plus 100, the enantiomer has to be minus 100. So here it is. This is ripped off from your textbook. There's the light source. There's a polarizing filter. So notice all these different vectors. Notice the filter is vertical. So only the vertical one gets through. Then in this tube, which is called a cell, is your sample. Notice how that vector is then tilting. It comes out, and then you as the observer or the instrument measures which way it's tilting, to the right or to the left, and then the magnitude. And so that's the instrument that's used to figure out which is which. So we've calibrated ourselves. We have a pure enantiomer and then the other stereoisomer. So pure and pure. That's fairly straightforward to understand, right? One's plus, one's minus. But what about everything in between? So the midpoint, where you have a 1-to-1 mixture of them, is called a racemic mixture, or a racemate. If you measure the specific rotation of that on a polarimeter, the value is going to come out to be exactly 0. So if you think about your enantiomer that's plus 100, your enantiomer that's minus 100, so the instrument goes this way, then it goes that way, and they add each other to 0. So now we have 3 points. And so really we need to then figure out between a 1-to-1 mixture and completely pure, how does that affect the specific rotation? So the equation that's used is this alpha value in square brackets. The square bracket here does not mean molarity. It just means that your observed rotation of alpha has now been normalized according to the concentration C times the path length, which is typically 10 centimeters. So really experimentally, what I do and what my students do in lab, you make your concentration 1. You're using a path length of 10 centimeters, which is 1 decimeter. So really the denominator ends up being 1. So here are the different factors. Normally, temperature, it's ambient or room temperature. Wavelength is 540 maybe nanometers. It's a sodium lamp. So when I was a kid, the street lights on my road were sodium arc lamps. They have like a yellow glow to them. When those came on, you went inside and ate dinner. That was sort of the end point of playtime, but it's sort of like a yellow light, again, that gets polarized. Observed rotation, concentration, and path length, they go into that, and then the instrument spits out your specific rotation. So if you see a sign that's plus, that means the light has been rotated clockwise, which is dextrorotatory. And then the old-timey literature, it's italicized D. If the light is counterclockwise, it's negative or levorotatory and italicized L. So I refer to those as small d, small l, because on Wednesday we'll talk about big D, big L, which means something completely different in terms of stereochemical nomenclature. But what I really want to emphasize, R and S is what you determine from your model. Plus and minus is what's measured by the instrument. So again, plus or minus on the exam will be given to you, or you'll have to go somewhere and find it. Not too much of a treasure hunt, but some searching. Any questions so far? Yep. So again, if the sign is plus, then yes, that light has rotated clockwise. But that does not correlate exactly to the R stereochemistry. R and S is what you figure out on your own. And really, if you're thinking sort of 2 steps ahead like chess, this is a big issue in organic chemistry is, yeah, you can draw something, assign R and S, and then measure the optical rotation, but have you really absolutely assigned the rotation to the correct enantiomer? So you sort of know the basics at this point, but experimentally it's very difficult. This process, I mean, it's a long process to do it. So again, enantiomers will have the opposite sign, and the magnitude is whatever it is the instrument spits out. If you have a racemic mixture, the specific rotation is 0. But now there's an issue of from 1 to 1, the racemate, to either of the pure enantiomers, how do we describe those systems? And the concept that's used is called enantiomeric excess, or EE. And this is primarily what every organic chemist walking the earth studies nowadays, is reactions that will produce high EE. And again, pay attention to this because it can be a little confusing with the logic of what that means. In the classical sense, the way you would measure it is simply by taking the observed rotation of whatever mixture you're dealing with and then dividing by the specific rotation of the pure enantiomer. So that begs the question, do you know that the value you measured for the denominator is that of 100% of one enantiomer? Because otherwise your values will be off. So for everything that we'll do in here, those values are sort of known. And then you multiply by 100, and that gives you the excess of one enantiomer over the other. So that will hopefully be a little bit clearer as we look at some tables in the next upcoming slides. So if you did not have a polarimeter, another way that you can do this is using moles. So again, moles is the concept or term that sort of normalizes everything when you're dealing with like individual weights or amounts. You take the molecular weight, do that conversion, that gives you moles, so everything's sort of normalized. Another way to calculate is moles of one enantiomer, subtracting moles of the other, divided by the total moles. Well, that will also give you the same value. So nowadays, like in my lab, for instance, we use an instrument called HPLC, which is high performance liquid chromatography, with a stationary solid phase that's chiral that will separate these things into two different peaks. You get the area of those peaks, and then you just shove it into this equation here. R minus S divided by R plus S. And the numbers come from Beer's law. Does that sound familiar from Gen Chem? So this is Beer's law relating to absorbance. So while I grab a sip of liquid here, take a look at this table and see if you can understand sort of the math that's going on. I've just shown it for R being the major, but it holds true the other way around if S was the major as well. So we'll look at the first 2 points here, and then we'll look at everything in between. So if you had 100% R, that means there is 0 S enantiomer present. So you have 100% enantiomeric excess. So let's look at the last entry. You have 50-50 or 1-to-1. That's 0% enantiomeric excess, which means you have 100% racemate. So again, everything in between here, and I've only given you, this 1, 2, 3, 4, 5, 6 or 7 scenarios, but this will go all the way down to 51, basically. So in my mind, I always have to take a second and think about this because it's a smidge confusing. If you have 99 to 1, that means the excess of the R is 98. Because that one S takes away one of those R's. So you have 2% of the racemate. So 98 parts. So let's think of R and S in these first two columns as parts. They have to equal 100. And then the third column is your enantiomeric excess, in this case of the R. So 98 to 2, those two S's subtract off 2 from 98. That gives you an excess of 98% R. So overall, 4% of that is the racemate. So I'll just highlight right here. So scientific research being what it is, that number I highlighted, that's the gold standard to get research published nowadays. Any reaction that you run, you're typically shooting for that standard to get published. So again, you can just follow the numbers from, going down there, 74, 73, 72 to get down to the 50-50. Any questions on this table before we move on? So why is this important? So here's a molecule of the lecture called thalidomide. And thalidomide is an immunomodulatory drug. It has multiple therapeutic indications. And that means basically what area is this targeting in the body, what's it acting upon. So that's a sedative, anti-nausea, chemotherapeutic, and leprosy. Nowadays, it's sort of used as a anti-cancer agent. But back in the 40s and 50s, it was used and marketed to pregnant women as an anti-nausea drug. So one of the symptoms of being pregnant is morning sickness, where you can't hold anything down and you're puking a lot. And so that's not good for the development of a fetus that needs nutrients to grow. And basically, what was found out, as you can see in this old-timey package here, is that women that were taking thalidomide when they were pregnant were having babies born with, as you can see in the limbs, the arm and the leg there, a defect. So any drug that produces a malformation in an embryo is called a teratogen. And the specific defect for thalidomide was phocomelia, and I think they call it seal limbs, like your arm, the arms don't grow out, they're sort of like not developed properly. And what's interesting, if you read the story about this, they pinpointed like the exact days of fetus development in which this happened when women were taking thalidomide. I think it's like days 23 through 29 is where the cell division of this was inhibited improperly or something that led to this. So pretty early on, basically. And society being what it is, the business fought it. The doctor said, hey, you got to pull this from the market. So that's when, these government institutions that serve us, like the FDA, get involved and say, look, you can't market this towards this indication anymore because these babies are being born this way. I mean, even if it's one baby, that's one too many, right? So there's no actuarial science that will justify keeping this on the market. But nowadays it's used with people that have a specific type of cancer. So what we want to do is, if we look at the molecule, can you see a stereogenic center in there based on sort of how things are drawn? So let me, we'll sort of walk along a ring, and I'll give you some clues to help you out. If we start right here at that carbonyl group, it's sp2 hybridized. So right off the bat, it does not have 4 substituents, so you don't have to consider it. Nitrogen has 3 substituents. So we move along, another carbonyl. Is this a stereo center right here? Why not? It has 2 hydrogens. This also has 2 hydrogens, so that's not a stereo center. That carbon right there is a stereo center. It has a carbon, a nitrogen, a hydrogen, which I haven't shown, and then another carbon. But then you'd say, Donahue, you're breaking the rules here. Carbon is carbon, aren't they the same? When you're looking at, when I say substituent, I don't just mean like the exact next atom. It's like everything that's bonded to that. Since this is sp2, and it's a carbonyl, that's sp3, it's a methylene. Those are different substituents. So we move just beyond the fact that they're both carbon, but what's actually their functional group. So what you'll see in your book is that stereocenters are typically identified with an asterisk. So we have one stereocenter. That means one of them is R and one of them is S. So the question states, the S enantiomer of thalidomide was ultimately found responsible for these birth defects. So the R enantiomer does not cause these effects. So that's kind of interesting to think about. So which one of these is S? So there's our stereocenter. I've drawn in the hydrogen. Now keep in mind what a common pitfall for a lot of students. When you apply these rules, you are only going out to the directly bonded atom to that stereocenter. What I mean by that is you're looking at that carbon, that's your anchor point. Don't let your eyeball go out to there or to there. So first let's see, what do you think? A or B? Huh? So we think B. Let's test it out. So we have, I'm just going to say CSP3, CSP2, N, and H. So those are the 4 atoms directly bonded. This is the way I think about it. Write out a little periodic table, then we want to assign priority. H is the lowest atomic number, so that's going to get priority 4. The dashed line means it's pointed away from you, so we're good with that part of the rule. 2 C's and an N, so N's going to get the highest priority of 1. Now we have carbon-carbon. So if they're both atomic number 6, what do we need to do? Did anyone read the book? So these are both carbon. If they're both atomic number 6, what's 2 and then what's 3? Basically what you have to do then is apply the same rules to each of them. What are they bonded to? H, H, and C. Then from those 3, you figure out which one has the highest atomic number. But the double bond is kind of weird. So we have to do something sort of different with that. So carbon, we consider each of those oxygens as separate. So we would draw it like O and then O. So 6, 7, 8. So we have 7, 8, 8. We can see that when we compare these numbers, 6, 1, and 1, 7, 8, and 8, that carbon bearing the 8 is going to take priority. So that gets 2. So we have 1, 4, 2, and 3. So what order do those go in? So that's clockwise, so that will be R. Because A is the exact mirror image, that has to be S. So thalidomide was sold, prescribed commercially as a 1-to-1 mixture of R and S. It was found that the S enantiomer was responsible for the birth defect. So why couldn't the company just take then the pure R enantiomer, rebrand it, and then sell it as an anti-nausea drug? The issue is, if you take the pure enantiomer, the pure R enantiomer, you dose it into a human, it racemizes back into the 1-to-1 mixture, producing the S, which produces the birth defect. So how does that happen? So it happens using stuff we learned earlier in this module. See that hydrogen I just drew in there? That carbon next to the carbonyl is called the alpha carbon. So that CH bond is more acidic than normal. So it looks like a ketone almost. So those are a pK of about 20. And what will happen is a base will come along and deprotonate that. So once it deprotonates that, it has a resonance form. And now we know that an sp2 hybridized carbon is flat. And so when it gets reprotonated, it can protonate from the top or the bottom. And that's going to lead you either to the S or the R enantiomer. So even though it might have been sold as one enantiomer, under the conditions in the body, it racemizes to 1-to-1. So that is just an acid-base reaction. So nowadays, with the Food and Drug Administration being what it is, a lot of this stuff has to be proven before a drug can ever make it to market. So if you ever hear the term clinical trials, the first clinical trials are done in healthy humans. You can go on the FDA website, see if you can make a couple $1,000 for trying out a drug. If you start throwing up immediately that the drug is not going to go anywhere, that's the first indication that it's not going to pan out. If it makes it past phase 1, then it goes into phase 2, which are people that I believe are sick with whatever disease and really need that treatment. It's a small group. And then phase 3, which is where they spend a lot of money and they get thousands of volunteers to test it out on a bigger population. So it takes about, 10,000 or more drugs before one actually makes it through that process. So they screen a lot of compounds. So if you've been prescribed something, thousands of people before you it's been tested on. So you can be reasonably certain it's going to do what it says it does. So let's do some problems where we think about specific rotation and excess conceptually. If the S enantiomer has a specific rotation of negative 62.6, what's the specific rotation of the 1-to-1 mixture? It's got to be 0. And then the specific rotation of the pure R enantiomer is what? So it's plus 62.2. So those are again, the three sort of main calibration points. So again, we need to, as Ms. Jurasevich, my kindergarten teacher, said, put our thinking caps on. Again, it's not just the wording of these questions that's confusing. You really have to calibrate yourself to what it's asking. So we know that the pure S is equal to negative 62.6. If the pure S has undergone partial racemization, not full racemization, and we measure that value to be negative 31.3, the question is asking you here, it's not this column, but sort of these first two. What are the parts, R to S, in that mixture?
What do you think? So I like to use a little diagram like that to help me out and sort of calibrate me on which side of the zero I want to be on. So notice the number is still negative, right? Negative 31.3. Really what that's telling you is you have to have more S because the number is still negative. And then 31.3 divided by 62.6 is 50, right? But the question is asking you not about the excess, but about the parts. So to get to 50, the right answer would be D. You have 25 parts of the R that are canceling out 25 parts of the S. That gives you the 50. So the 50 is the enantiomeric excess. And that's, again, derived from 25 to 75. So should you encounter this in the book or on the exam, again, that's a way to think about it to put you on the right track. We have 2 minutes that I want to use, so don't start packing up yet. Any questions before we move on to the last 3 slides? So as a preview for Wednesday, here is that molecule AZT, which we started off the course with. So looking at that molecule, you do your test of each carbon atom. Does it have 4 substituents? How many stereogenic centers does AZT have? So I would say if you start along the backbone here, just go along the rings. So that is not a stereocenter. It has 2 hydrogens. Is this a stereocenter? So that one is. What about this one? So that's a stereocenter. The next one is not, has CH2. That one is. You go along the rest, they are not. So we end up with 3 stereocenters. And then you have to assign R and S to them as they are drawn. But if either of them can be R and S, we have another little equation to know. 2 to the n, where n is the number of stereocenters. So AZT can have 8 possible stereoisomers. And so we'll talk about on Wednesday, when you get into this situation with more than one, you're still assigning R and S, but then what are these other relationships? So for example, those would be enantiomers. But what if one of them differed? What's that relationship called? So we'll talk about that nomenclature, and we'll look at some specific systems and introduce one or two more topics then. So sorry about going over, but that's